Hello, welcome back, and thanks for clicking on another Anarculus production, a very exciting event. Today we are going to talk about optimization as well as the second derivative test, which we've kind of been ignoring for an entire chapter, at least half a chapter, okay? Because everybody thought the second derivative test was the one for concavity. That's not actually the second derivative test, but today all will be revealed. So an exciting event coming up in just one slide. So here we go. It's time for that second derivative test. Okay, here is the second derivative test. The second derivative test allows us to find the mins or the local mins and the local maxes, okay, of a graph using the second derivative as opposed to the first derivative. So far, whenever you were looking for relative mins or relative maxes, right, you find the derivative, set it equal to 0, find the critical numbers, put it on the chart, and then compare the chart with f prime, right? We can even put it down here. You find the derivative, set it equal to 0, find the critical numbers, put the critical numbers on the chart, right, x equals a, x equals b, then go from negative infinity to a, from a to b, from b to infinity. Then you want to know stuff about f prime, so you can figure out stuff about f. Okay, so if you got something that's bigger than 0 here, you'd say, oh, that's increasing. Less than 0, oh, that's decreasing. Bigger than 0, oh, that's increasing. Okay, and then you would say, all right, well, x equals a then is a max, rel max. X equals b, oh, that's a rel min, right? That's how you found mins and maxes thus far, okay? That's the first derivative test. Now, the second derivative tells you about the concavity of the graph, okay? Whether the graph is concave up or concave down. The second derivative test says that you can use the concavity of the graph to determine whether or not the function has a local min or a local max at a critical number. Okay, and here's how it works. It's actually a pretty simple concept when you see it, okay, in front of you. If, and I know there's some information up here, but I think it's a little more clear if we put it like this. If f double prime of, let's start again. Let's do this. If x equals c is a critical number, okay? X equals c is a critical number. That means that f prime of c has to equal 0, right? That means the derivative has to equal 0 at some number, okay? That would mean x equals c is a critical number. And the following happens. If you find the second derivative and you plug c in, you take the second derivative and you plug the critical number into the second derivative, and you get something that's bigger than 0, okay, then what does that mean? That means f is concave up, right? Because the second derivative is positive. When the second derivative is positive, then f is concave up. But what does concave up look like? It looks like a U. So then the point at x equals c has to be a relative min. Look at the graph. Look at something that's concave up. Okay? It looks like a U. So this point at x equals c has to be a relative min because f is concave up. Okay? It works the other way as well. I'll see if I can put it in up here. All right, so we'll see if we can add something to this. If f double prime is less than 0, let's add to it. Then f is concave down. But concave down looks like this. So what does that mean? Then x equals c, the critical number, has to be a local max. There it is. You can see it right in front of you. Okay? You can literally see it. If the second derivative is less than 0, then f is concave down. concave down looks like this. So that means that point at x equals c, or that critical number, has to be a local max. All right, what's important to understand about the second derivative test is the following. You must have a critical number, okay? You first have to figure out that the derivative is equal to 0 at that number, right? It has to be a critical number, because if it's not a critical number, it can't be a min or max, okay? It's got to be a critical number first, all right? Otherwise, you can't use the second derivative test. It doesn't make any sense. Now, there is one extra thing that we need to add on here quickly, okay? It's the following, and this is the problem with the second derivative test, and one of the reasons why I don't show it to you until the very end of the chapter, okay? It's this. If the second derivative at x equals c, and you may have, seen the idea, or see what I did there, Steen? If the second derivative at c is equal to 0, because if it's less than 0, then f is concave down, right? If it's greater than 0, then f is concave up. The problem is when the second derivative is equal to 0, it's not concave up or concave down. So then what do? Then the problem is the second derivative test fails. And you have to use the first derivative test. Okay? The second derivative test doesn't work. You have to go back to the first derivative test anyway. So one of the reasons that we spent so much time using the first derivative test, at least during the chapter, was because a lot of times that second derivative test, when you were going to make graphs, it would have failed anyway, and you would have been forced to make the chart no matter what. So just to save time, we just made the chart. But in this lesson, you're pretty much always going to get a result, all right, which is why I show it to you here. All right, so let's see this in action, okay? Here it is formalized, all right? So these are issues that you can have with the second derivative test. The first derivative, it doesn't exist. If the first derivative is undefined, it's not going to exist in the second derivative either, okay? All of these, you'd be forced to go back to the first derivative test in all of these scenarios. But that's not really what I'm interested in here. I'm really more interested in can you actually use it properly, all right? Because otherwise I wouldn't ask you to do it. All right, so let's use the second derivative test to figure out if there are any relative extrema. So the second derivative test, the first thing it involves is finding the derivative and setting it equal to 0 to find the critical numbers. So to find the derivative, we'd get, let's see, 2x squared plus 5x minus 12. And I need to set that to 0, okay, to find the critical numbers. All right, so this probably factors 2x and x. Let's see, we could have 6 and 2, 4 and 3, looks like 4 and 3, plus 4 minus 3. If I FOIL that, do I get back to where I started? 8x, 5x, yep. Okay, so this is how it factors. So let's split these, and we get x equals 3 over 2, and x equals negative 4, right? So these are my critical numbers. Here are my critical numbers. All right. And again, on the exam, on the AP exam, this would be the first thing you would have to do. You'd have to convince the reader that these values are critical numbers. Okay. Then you can go ahead and go to the second derivative and use the test. So the second derivative would be 4x plus 5. Okay. So now here's how this works. It's really simple. So all we're going to do is we're going to plug each critical number into the second derivative. So the second derivative evaluated at 3 halves is 4 times 3 halves plus 5, which is 11. So we get 11. 11 is positive. So f is concave up at 3 halves. So the graph looks like this. Then our conclusion is x equals 3 over 2 is a relative min. Okay, x equals 3 halves will be a relative min because f is concave up. All right. And then the same thing at x equals -4. So if we do the same thing, f double prime of -4 would be 4 times -4 plus 5, which is -11. Okay, that's less than 0. So f is concave down. So it looks like that. So x equals -4 is a relative max. And that's it. If you wanted the y values to go with these two x values, you'd take them and plug them into the original, right? And you could find the y values to go with them. But that's how you would find a relative min or a relative max using the second derivative test. Okay? All right, let's see one more here. So let's do the same thing. Let's find any local extrema. So first thing we have to do is find the derivative. So we get 4x cubed minus 16x equals 0. I can factor out 4x, and I'd be left with x squared minus 4. I can split these and solve them, or I could, it doesn't matter, I can do it either way. I don't know why I just wrote 4x equals 0, but you get x equals 0, and x squared minus 4 equals 0, x equals plus or minus 2. Okay? So now let's go, these are my critical numbers. All right? And again, on the AP exam, sometimes they'll ask you for explanations using the second derivative test. The first thing you have to do to use the second derivative test is convince the reader that the derivative is equal to 0 at the number that you want to use. Okay? Otherwise, you can't use the second derivative test. If it's not a critical number, you can't use the second derivative test on it. All right, so let's go to the second derivative here. The second derivative is just going to be 12x squared. No, minus 16, right? 12x squared minus 16. Okay, so now let's take each one of our critical numbers and plug them in. F double prime of 0 comes out to be -16. That's less than 0. F is concave down. It looks like this. X equals 0 is a relative min. If I find F double prime of 2, 12 times 2 squared minus 16. I don't know what that is, but I know it's positive. That's all I care about. So F is concave up. It looks like a U. X equals 2 is a relative max. And if I plug in -2, and 12 times -2 squared minus or 16, that answer is also going to be bigger than 0. So F is concave up. It looks like a U. So X equals -2 is also a local or relative max. Okay? And there it is. That's how you use the second derivative test. It's actually pretty simple. Like I said, the biggest pain is when you use the second derivative test and the second derivative comes out to be 0, then you're stuck going back to the first derivative test anyway. All right? All right, so now, coming up, your turn. Give it a try. Okay, now the second half of this lesson teaches you about optimization. All right? Optimization in the real world. So optimization is actually something that people could really see as being potentially something that exists out there that they could use. So a good example of optimization is, imagine that you're Mr. Campbell. I think you all know Mr. Campbell, okay? The soup guy, you know what I'm saying? All right, Mr. Campbell's soup, okay? So the one thing about Campbell's is he makes a lot of cans of soup, right? So one of the things you could understand about Campbell is something that Campbell would be interested in is if he wanted to put a certain amount of soup in each can, he would probably want to minimize either the size of the can or the amount of material that he needs to make the can, right? It saves him money, okay? The less aluminum or tin, whatever it is he uses, okay? The less money it's going to cost him, the more profit for him, right? That's what optimization is all about. Okay, this is the very basic building blocks of that. All right, so we're not going to get too in depth or too crazy. Okay, obviously you can make this much more complicated with a lot more variables other than just, I want to minimize the amount of material. All right, but it's just an introduction to it. All right, so that's what we're going to do. Okay, so here's how you solve an optimization problem. Okay, your goal will be to maximize or minimize a certain quantity subject to a given constraint. So for example, in my Campbell soup example, I want to minimize the amount of material I use for my can, subject to the fact that I have to have a certain amount of soup in the can. Okay, so this can's going to have to be a certain size to begin with. Otherwise, you won't be able to fit all the soup in it. All right, so to do that, here's what you're going to do. You're going to establish two things, an objective and a constraint. And sometimes it's useful to draw a picture to do that. Okay, you're going to write the objective equation in terms of one variable. Usually that means you have to take the constraint and sub it into the objective to make that happen. We'll see that in a few minutes. Okay, you want to find the min or max of the objective function. You know what to do there. To find the min or max, how do you do it? Find the derivative, set it equal to 0, find the critical numbers. Okay, those are your potential mins and maxes. And then we are going to use the second derivative test that we just talked about to confirm that the critical number is going to maximize or minimize that function. All right, so let's see it in action. Here we go, coming up, very exciting. Here's our first optimization problem. We have a farmer. Okay, he's creating a rectangular pen for his animals. Of course he is. And it has 160 feet of fence. Okay, that's what he's got. The side of a barn will be used for one side of the fence. Okay, so he doesn't need fencing on that side. So here's what he's got. He's got this barn here. All right, here's the barn. Okay, we'll put a door on it and everything. All right, and then what he's going to have is he's going to have the animals in here penned in like that. Okay, penned in like that. It's going to be rectangular. All right, so he doesn't need any fencing on the side that the barn's on. He just needs fencing on the three pink sides here. So let's call this side X, I guess, and we'll call this side Y. And let's see what he wants us to do. He wants us to find the length and the width that would produce the largest area for the pen. So largest area, he wants us to maximize this. So the objective, what does he want us to accomplish? He wants us to maximize the area of the pen. The area of this pink rectangular pen is X times Y. Okay. Now this is subject to some kind of constraint, right? What is constraining us in this problem? What's being forced upon us, so to speak? Okay. He has 160 feet of fence. So that means these three pink sides can't be more than 160. And theoretically, he probably wants to use all the fence. Why would he want to use only, 140 feet if he's got 160 feet? That way he makes the pen as big as possible for the animals. So the constraint is that X plus 2Y has to be 160. Right? If I add these three sides together, I have to get 160. Okay, so now you can see the issue. If you go back to the objective, I want to maximize X times Y. The problem with maximizing X times Y is there's two variables. When you find a min or max, we've never done it with two variables in there, X and Y. So I need to eliminate one of the variables. So to do that, I'm going to use this constraint. I'm going to solve the constraint for X just because it's easier. It doesn't matter which variable you solve for. In this case, it's just easier to solve for X. So X is equal to 160 minus 2W. And I'm going to sub that up here. So my new area equation is going to be X. Oops, nope, not X. It's going to be 160 minus 2Y times Y, which I'm going to multiply out, and I'm going to get 160Y minus 2Y squared. So now, what do I want to do with this? I want to find the max of this equation. How do I find the max? Oh, I find the derivative. So the derivative of A is 160 minus 4Y. Set it equal to 0 to find the critical numbers. I get Y equals 40, looks like. Okay, it looks like y equals 40. This is my only critical number. So it looks like it's the max, but I have to confirm it's a max. To confirm it's a max, let's go to the next derivative. So a double prime of y is equal to -4. Well, -4 is less than 0. Okay? I mean, if I plug 40 in, I'm still going to get -4, right? So a double prime of 40 is -4. That's less than 0. So a is concave down, right? A is concave down. It looks like an upside down U, which means that we have a relative max. Okay, we have a relative max here. So now, it wants the length and the width that will give us the largest area. We can find that. Let me erase my pen here. All right, let me erase my pen real quick. Okay, so to find the relative max, what we're going to do is we have y equals 40 is one dimension. To find the other dimension, we have x plus 2y equals 160. So x plus 2 times 40 is equal to 160. So x equals 80. And then the area will be 80 times 40, which is 3,200 square feet. Okay? So it's 80 feet by 40 feet and 3,200 square feet for the area. That is what the maximum area would be. All right? All right, let's try another one. Okay, now let's talk about money. We want to construct a box whose base length, okay, the length is 3 times the width. So we have a box. Okay, here it is. Here's how we draw it. There we go. Okay. We have length, width, and height. We know the length is 3 times the width. So let's put that down there. L is 3W. Okay, the material used to build the top and bottom of the box is $10 a square foot. So let me put that. This is $10 per square foot on the top and on the bottom. The sides are all 6 feet. So it's 6 feet for each one of these sides around, 10 on the top and the bottom. The box must have a volume of 50. Determine the dimensions that will minimize the cost to build the box. Okay, so this makes sense. Again, it's certainly possible that somebody might have to do this. All right, so the goal, the objective, our objective is to minimize the cost. So let's talk about the cost of the box. Well, the cost of the box is going to consist of us finding all of these sides on the box, right? All of these sides on the box, okay? So let's talk about all the sides. All the sides would be, let's see, we got, let's do the sides down here. So we have 3w squared, right? Because L is 3w. So we have 3w squared, okay? And then we have another 3w squared for the top. And then the sides are WH, another WH, and then we have an LH also, right? Okay, an LH. And then another LH, right? But L is 3W, that's right. So let me go back in here. So we have 3W squared. Oh, let's just start combining them. What the heck, right? YOLO. All right, so we have 6W squared plus 2WH plus 2LH, but L is 3W. So we have 6W squared plus 2WH plus 2 times 3WH. So that's going to be 6W squared plus 2WH plus 6WH. Okay, now let's talk about the cost. The 6W squared is the bottom and the top. it's $10 each for those. So we got $10 times 6WH plus we're going to have $6 for 2WH. And then we're going to have another $6 for 6WH, right? Okay, another $6 for 6WH. So that gives me a minimum cost of 60W squared, okay, plus 12WH and 36. 12 and 36 is 48WH. Okay, so that's what I want to minimize. I want to minimize that cost. All right, now subject to the constraint. So what is the constraint? So the constraint is the fact that the volume has to be 50. It tells you flat out, the volume's got to be 50. End of story. How do I calculate the volume? Well, length times width times height. So it's going to be 3W times W, 3W squared times the height. 3W squared H. Okay. Now, up here in my cost function, I have two variables. I want to knock it down to one. So I'm going to solve the volume formula for H. I'd get 50 divided by 3W squared equals H. Plug it in, and I'm going to have C equals 60W squared plus, let's see what we have. We have, oh boy. All right, so we got 3W squared is going in up here. So we got 48 times W times 50 divided by 3W squared. All right, so let's cancel some stuff. W and W goes away. 3 goes into 48 16 times. So C equals 60W squared plus 16 times 50 is going to be 800 over W. Okay, these two knock out, make 16. So 800 over W. All right, so now we're going to have to erase some of this stuff, okay, because I ran out of room here. So what do we want? Let me just erase all this. Okay, let me just erase a bunch of this stuff here. Oh, let me just erase the whole thing. 60W squared plus 800 over W. All right, so we got C is 60W squared plus 800 over W. All right, so now I want to find the minimum of this. So I got to find the derivative, set it equal to 0, find the critical numbers. Let me bring the W to the top here. It makes it easy to derive. W to the negative 1. Okay, so C prime is going to be 120W minus 800W to the negative 2. I have to bring that back down to the bottom because I do need to find a common denominator before I find the critical numbers, W squared. So that's going to be 120W cubed minus 800 over W squared. I need that to be equal to 0. So that's equal to 0 when 120W cubed minus 800 is equal to 0. So W will be equal to the cube root of 800 over 120, which is about 1.883. Okay, now my other critical number is when W squared is equal to 0, because the bottom can be 0, W equals 0. All right, now, here's the thing about optimization. The nice part about the word problems is W equals 0 makes no sense. There's no way that's going to be the answer because then you won't even have a box, right? If there's no width, if there's only 2 dimensions, you only have a 2-dimensional shape. You don't have a cube or a box, whatever it may be. So this is my only critical number. I want to confirm that it's going to be a min. All right, so now I have to go back and derive one more time. Let me just erase this so I have a place to find my second derivative. All right, I'm going to go find the second derivative. When I do, I'm going to derive this one up here. right? I'm not going to derive any of these. They have common denominators. Forget it. They're a pain. Just go back to the easier one. So you're going to get 120 plus 1600 w to the negative 3. So C double prime of 1.883 is going to be 120 plus 1600 over 1.883 cubed. Okay, I don't know what that is. I really don't care. The only thing I care about is that it's bigger than 0. So that C is concave up, which means that 1.883 is a min. It's a relative min. That's good. Okay, now if you want the dimensions, right, that'll make this happen for you. We know the length is 3 times the width. So take 3 times 1.883. That'll get you the length. And then you also know the volume. 50 was equal to, what was it? It was like 3w squared h, I think. So 3w squared h. So 50 is equal to 3 times, let's see what we got. W is 1.883 squared times h, and you can solve for h, and those gives you 3 dimensions. All right, so it's a little time consuming, but it's not too bad. All right, so here's one more final problem. A rectangle is bounded by the x and y axes, and the graph of y equals 6 minus x over 2. There's the graph there in red. It's that line. What length and width should the rectangle have so that its area will be a max? All right, so what I'm asking you is, I'm asking you to fit a rectangle, okay, inside of this region. I want the rectangle to be a max. So I want you to maximize, here's my objective. I want you to maximize the area of a rectangle. The area of this rectangle is just going to be x times y, because I go x units over and y units up. Right? Okay, x units over, y units up. The constraint is going to be that the rectangle has to be bounded by the x and y axes and this graph. So I know for certain that y equals 6 minus x over 2 because some point on this rectangle has to be on this graph somewhere, right? It's got to be there. Okay? I mean, it's silly for me to make my rectangle like this. There's no way I'm going to maximize it, right? So I definitely want one of my points to be as far to the right as possible, which means it has to be on the graph. Okay? All right, so now the question is, what do we do with that? So let's go back here. I want to take this and substitute it in up there. It's already solved for a variable, makes my life easier. I'm not going to solve for the other variable. So a equals x times 6 minus x over 2. So if I clean that up a little bit, distribute the x, I'm going to get 6x minus x squared over 2. So now I want to derive this. So a prime is going to be, just leave the 1/2 out of it, right? Its derivative is going to be negative 2x. Derivative of 6 is 0. Okay, so what do you get? You get negative x, right? Oh, no, I'm sorry. Sorry, folks, I forgot. I'm missing an x. You guys are probably yelling at me that I'm missing the x. I'm missing the x. Okay, all right, let me go back here one more time real quick. One more time, sorry. Real quick, just write it over so that people can see it. Distribute the x, you get 6x minus x squared over 2. All right, now let's find the derivative. Makes more sense, way more sense. Leave the 1/2 out of it. You get 6, derivative of 6x, minus 2x. Set it equal to 0 to find the critical numbers. So you're going to get x equals 3. There's your critical number. So now, is it going to be a relative max? That's the question. Let's go to the next derivative. So a double prime of x will be, leave the 1/2 out of it. The derivative of negative 2x is a negative 2. So that equals -1. So a double prime of 3 is -1. That's less than 0. So a is concave down. So it looks like that. So yes, this is a relative max. So now, that's a relative max. What length and width should the rectangle have so the area is a max? If x is 3, then y is equal to 6 minus 3 over 2. Then y should be 3 over 2. So what we are saying is the following. If I put a point at x equals 3, y equals 3 over 2, 1.5, and I draw this rectangle, this is the largest rectangle that I can fit, okay, in area that's bounded by this curve. Okay? And that's it. We're all done. We did it. All right. Thanks for clicking, folks. As always, have a great day.